Okay, this video is going to cover Chapter 4 of the book, Discrete Random Variables and Probability Distribution. After completing the chapter, the goals are that you should be able to interpret the mean and standard deviations for discrete random variable, use binomial probabilities, binomial probability distributions to find probabilities, describe when to apply the binomial distribution, use hypergeometric and Poisson discrete probability distributions to find probabilities, explain covariance and correlations for jointly distributed discrete random variables, and explain an application to portfolio investments. Here we have random variable. It represents a possible numeric value from a random experiment. Now, random variables can be discrete, i.e. where they have numbers 1, 2, 3, or they can be continuous, where it could be 1, 1.111, 1.1112, 1.1113, etc., where it's continuous and there's no real intervals, or the intervals are very small. And we have here, which looks a very symmetric distribution, and our discrete random variables here on the left-hand side. We're going to start with discrete random variables. We'll talk about continuous random variables in Chapter 5. Discrete random variables take on no more than a countable number of values. Right? For instance, we have two examples here. The first is with dice. I roll a die twice, and I'm going to let X be the number of times 4 comes up. So basically, anytime 4 comes up here, right, we have a success when we tell it 1. So in this case, since I roll it twice, X, the number of times 4 comes up, can be 0. It doesn't come up at all. 1 or 2. The other example is I toss a fair coin 5 times, and I'm going to let X be the number of heads. Now the possible number of heads are going to be, it's possible that I get all tails, so it could be 0 heads. It could be 1 head, 2, 3, 4, or all 5 of the times I toss a coin, it can come up heads. Those are the possibilities. And we're going to see those a little later. Those are basically the sample that we're talking about. Okay. Continuous random variables that we'll talk about in Chapter 5 can take on any value in an interval. Possible values are measured in a continuum. Examples: weight of packages filled by a mechanical filling process, right? The temperature of a cleaning solution, and the time between failures of electronic components. How long does it take that electronic component to fail? Right? So now we're going to let X be a discrete random variable, large X, capital X, and we're going to let small x be one of the values in X, in capital X. The probability that a random variable X takes on a specific value, small x, is denoted by the probability big X equals little x, or capital X equals small x. The probability distribution function of a random variable is a representation of the probabilities for all possible outcomes. Now, in general, we can show this algebraically, graphically, or with a table. Here, we're going to show it first with the table and then graphically. So here we have a table with the probable outcomes for tossing a coin 2 times, right? I can have 2 tails, right? That means no heads, so 0 value. And that'll come up 1/4 of the time, so 1/4 or 0.25. I can have the first coin be tails and the second toss be heads, or I can have the first toss be heads and the second toss be tails. So in both those cases, I get 1 head right here. So that's 2 out of 4, or 50%, 0.5. And then finally, I can have both of those tosses be heads, right? And in that case, I'll have 2 heads, and the probability of that is 0.25. This is the table we're talking about. And graphically, we can see it here. Here's the probability. Here's a 0.25% probability, or 25% probability that we have 0 heads, a 50% probability that we have at least 1 head, and a 25% probability that both times we toss a coin, heads will come up. So probability distribution, we're going to require 2 things of probabilities, or if you think about it, these 2 things have to be. First, probabilities have to be between 0 and 1. That means the probability has to be greater than or equal to 0 or less than and equal to 1. The individual's probabilities have to sum up to 1. So if I take all the probabilities, just like we did before, I had 0.25 possibilities of 0 heads, 50% probability of just 1 head, and 25% probability of 2 heads. I add those up, 0.25, 0.5, and 0.25, and I get 1. Just in case I said that too fast. So I have 0.25, sorry, it's plus 0.5 plus 0.25, right? Equal 1. And of course the summation is just, or the summation sign is simply over the thing. It just tells us that we're going to sum all the probabilities together. And we sum all the possible probabilities together, it has to equal 1, just like in our example. A cumulative probability function. A cumulative probability function denoted by big F of x0 shows the probability that x does not exceed the value of x0, where the function is evaluated at the values of x. So here we have read back to our example, right? 0.25, right? That's first x, 0.25, 0.75, and 0.1. Now, if we had, let's say, I'm going to cheat a little and show you a distribution for chapter 5, or a cumulative probability distribution from number 5. Here, let me erase that. I can't even draw a straight line here. Pretend that's a straight line, and pretend that is our cumulative density distribution. Now over here, right, we're going to have the probabilities, and basically the probabilities here is going to show the probability that something happens here, the probability I have is something here with near the mean or the median, and of course the mean we talked about last time is just the average, and what's the probability that it adds there on the tails. Now if I add up all the probabilities, right, I get my cumulative distribution function. I add up all of these probabilities along the function, along the graph, along this bell-shaped curve. I add all those up, all the possible ones up, and it has to sum to 1. In our example, which is just a binomial example, right, it also sums to 1. The probability that it's 0 is 0.25, the probability is 1 is 0.5, and the probability that 2 heads come up is 0.25. So I have 0.25 is the first probability. I add that to having 1 head, which is 0.5. 0.25 and 0.5 give me 0.75. And then finally, I add the 0.25 to the 0.75, and I get 1. Those are all the possible outcomes, and the cumulative distribution, again, cumulative means you keep adding up, has to equal 1. So the cumulative probability distribution function, if I take all possible outcomes, has to equal 1. Okay, derived relationships. The derived relationship between the probability distribution and the cumulative probability distribution. Right? Here I'm going to let x be a random variable with probability distribution function p of x and cumulative probability distribution function f of x0. Then f of x0 is going to be the summation of all the probabilities of x that are less than or equal to x0, just right here. Right? So basically I sum up all the probabilities up to x0, right? And that'll give me the cumulative probability distribution function up to x0. So if I have my bell-shaped curve here, and I have some value, we'll call it here on the horizontal axis. I wish I could draw that a little straighter, but it's hard. So basically, if I have x0 here, my cumulative distribution function will be everything, all the area under the curve up to x0. And that'll be the function, and we know that since it doesn't cover, well in this case, it doesn't cover all the possible functions of x0 or all the possible outcomes of x, then we know that the cumulative distribution function is going to be less than 1 because there's positive probabilities out here past x0, at least in this example. Again, the notation that summation is over all possible values of x that are less than x0, if you didn't get that before. So our derived properties of our cumulative probability distributions for discrete random variables. I'm going to let x be a discrete random variable with cumulative probability distribution function f of x0. So basically what we did before, but this time with discrete random variables. So f of x0 is going to be between 0 and 1. That means it has to be greater than or equal to 0 or less than and equal to 1 for every number x0, for any x0. And for an x0 less than another number, we'll call it x1, the cumulative probability distribution has to be less for f of x0 than f of x1, or the cumulative probability distribution has to be less than or equal to f of x0 has to be less than or equal to f of x1. Okay, more properties of discrete random variables. The expected value or mean of a discrete random variable, we did means in chapter 2. So here we're going to say that the expected value of x is going to be mu, and mu is just a Greek letter. It looks kind of like a U right here, right? That's mu. And that mean, right, is going to be equal to each value times the probability of that value, summed up. So I sum them all up, x times p of x, and that gives me my average, or the expected value of x. For instance, here, going back to our example, I toss 2 coins, and x in this case is going to be the number of heads, just like before. I compute the expected value of x, right? And just like before, the expected value of x is going to be 0 times 0.25 plus 1 times 0.5, because there's basically 2 ways I can get 1 head. It can be on the first toss or the second toss, but there's 2 ways. And then finally, it's possible that both tosses are heads, and that's 0.25. I sum that up. 0 times 0.25 is 0, times 1 plus 0.25 is 0.5. 2 times 0.25 is 0.5. 0.5 plus 0.5 equals 1. You think of that again, 0.5, right here, 1 times 0.5, 0.5. Here, 2 times 0.25. Okay, let me erase that. Again, PowerPoint does that sometimes. Two times 0.25 is also 0.5. And of course here, 0 times any number is just 0. So here I'm going to have 0. So I have 0 plus 0.5 plus 0.5. equals 1. So I have 0 plus 0.5 plus 0.5, and that equals 1. So, like before, we talked about the expected value being the mean, and again, that is probably the most important thing you're going to learn in this class. I mean, the next most important are variance and standard deviation. The variance of a discrete random variable x, right, we can write as the expected value of x minus mu, where mu is the expected value or the mean, quantity squared. Or I can write that as a summation of each x minus the average. Now the average is going to be the same for everything in the samples, because it could be the average of the sample squared, times the probability of x. Right? I can also express this, since mu is a constant, as the expected value of x squared minus mu, so the summation of x squared times p of x minus mu squared. Right? And that's the variance. Now, when we want the standard deviation of the variance, all we do is take the square roots. I take the square root of the variance, and I get the standard deviation, which we denote as just sigma, and the variance in general we denote as sigma squared. So the standard deviation of the discrete random variable is going to be the sum of all the x's minus mu squared times the probability of each x. Okay, again, back to our example of the coin, where x is the number of heads. I want to compute the standard deviation. So here we go. So the number of heads, one of the possibilities is 0 minus 1. Now we know that the average here is going to be 1, or mu is 1. So 0 minus 1 squared, so it's just going to be minus 1 squared, which is positive 1 times 0.25. So, and then for the second one, it's possible that we get 1 heads, and that the probability of that is 0.5. So 1 minus 1 squared. This 1 minus 1, as you probably already figured out, is 0. So this is just going to be 0 squared. 0 squared is just 0 times 0, or 0. And again, 0 times 0.5 is still 0. And then finally we have 2 minus 1, which is, this is positive 1 squared. Positive 1 squared is just 1, times 0.25. So I have 1 times 0.25 plus 1 times 0.25, or 0.25 plus 0.25 gives me 0.5. So that is the variance of our coin toss, is 0.5. I take the square root of that, and I get 0.707. Now you can do this with the calculator to get the square root of 0.5, but it's basically 0.707. That is the standard deviation of our example of the 2 coin flips. Okay. Next, if p of x is the probability function of a discrete random variable, x, that we have, and g of x is some function of x, so basically if I have a function of x, right, I can get the expected value of that function of x as follows. The expected value of g of x is just going to be the summation of g over x, of g over all x, times the probability of each individual x. So this is basically, if I have x and I transfer it into a function, I can get the expected value of that function. Next, we're going to talk about linear functions. And basically, later on, or maybe if you take another MECU class, another statistics class, you might do linear combinations or regressions. In this case, we have basically a linear function of x, and I'm going to assume that x has expected value, or mean, mu of x, and variance, sigma squared x. I'm going to let a and b be constants, and I'm going to let y be a function of x, where y is equal to a, which is a constant, plus b, x. and of course b would be the slope of the relationship between y and x, and a would be the intercept. What this means is the mean of y is the expected value of a plus bx, and of course a plus b, the expected value is just a and b because they're constant, they don't vary. So it's going to be the expected value of a plus bx is going to be a plus b mu of x. That's the expected value. For the variance is simply going to be a plus bx is simply going to be, since the variance of a is going to be 0. Why? Because a is a constant and it's by itself. So basically, since it's by itself, the constant doesn't vary, a doesn't vary, so its variance is 0. Okay. Next, I have the variance of b of x, and the way we're going to do that is I basically going to square b and take that times the variance of x. So the variance of y is going to be b squared, which is basically the slope of x in our function for y, times the variance of x. What that means is that the standard deviation of y is the square root of this. So basically it's going to be the absolute value of b. The square root of b squared is just b, times sigma x. So it's going to be the absolute value of b times the standard deviation of x. Okay. Since a and b are constants, any constant, right? The expected value of a is just a, and the variance of a is 0, as we just saw. If a random variable takes on a value a, it will have mean a and variance 0. Basically, the mean will be just the constant since it doesn't vary, and since it doesn't vary, it's not going to have any variance. The expected value of bx is going to be b mu x, and the variance, as we just saw, is going to be b squared sigma squared x. And of course, the expected value of bx, its mu is equal to the expected value of x. That's the expected value of bx, just like here, is going to be b times the expected value of x. And we know that the expected value of x is simply mu of x. Next, we're going to talk about different types of probability distributions. For this class, we're going to do discrete, and I'm going to leave continuous distribution functions for chapter 5, the next lecture. The discrete probability functions that we're going to talk about are going to be binomial, and we're going to have two here. Basically, the Bernoulli and the straight binomial. The Bernoulli is just a one sample distribution function where the binomial can have more than one trial. We're going to talk about the Poisson trial and the hypergeometric. In chapter 5, we'll talk about different continuous probability distributions. We're going to talk about uniform, where basically the cumulative probability distribution function is basically just a straight line, and it's basically all the area under that straight line. Thanks. We're going to talk about the normal, which we saw as that bell-shaped curve, and the exponential, which will be similar. But we're going to, for this chapter, we're going to talk about discrete probability distributions, and we'll start with the binomial. And the simplest binomial is the Bernoulli distribution function. Here we're only going to consider one trial, and we're going to have two outcomes. It's either we're going to have success or failure, 1 or 0, or whatever it might be, heads or tails. I'm going to let P be the probability of success, and 1 minus P be the probability of failure. So my random variable X is going to be 1 if I succeed, and 0 if I fail. 1, 0. So then the probability distribution function is going to be as follows. the probability of failure, P of 0, is going to be 1 minus P, where P is the probability of success. That's P of 1 is P. And then, of course, the probability of failure is 1 minus that, 1 minus P. So if I'm successful, the probability of being successful is P. That means the probability of failing is 1 minus P, because probabilities have to equal 1, or the summation of probabilities have to equal 1. And here there's only two possibilities, either success or failure. Mean and random variances of a Bernoulli random variable. So here, for the Bernoulli, right, the mean is just going to be the probability of success, right? Because failure, of course, is, right, 0. That's the way we count it. So the probability is simply going to be P. Doing that algebraically, mu of x is, of course, the expected value of x, the summation of x, px. So the first x is 0, times the probability of failure, which is 1 minus P. 0 times any number is 0, so that's 0, plus the success, which value is 1, times the probability of success, which is P, so 1 times P, 0 plus 1 times P, or P. The variance for the Bernoulli random variable is going to be P times 1 minus P. Right? I take the variance, the expected value of x, minus mu of x is a summation of u minus x times P of x. So the first one, right, the probability, or the value for failure is 0, minus P squared times the probability of failure, which is 1 minus P. So here I have minus P squared, and of course that's, if I square a number, I get a positive number, so that would be P squared, right, times 1 minus P. And over here, right, I get the value for success, which is 1, minus the probability, or minus the expected value, u of x, which is P, and squared. So here I have P squared times 1 minus P. Here I have 1 minus P squared times P. I do the algebra, right? Here I have P squared times 1 minus P. Here I have 1 minus P squared times P. So here I have P squared times minus P cubed. And over here, I'm going to have 1 minus P times 1 minus P. I'm going to have 1, right, minus P minus P squared. So I do all the algebra, and what I end up getting is P 1 minus P. Okay. With the Bernoulli distribution, we do combinations like we did in chapter 3. So the number of sequences with SSSs and n-independent trials. I'm sorry, this isn't Bernoulli, this is regular binomial. We left Bernoulli. And Bernoulli was just one trial. Here, in a binomial distribution, we can have more than one trial. So the number of sequences with a regular binomial distribution with more than one trial, right? I'm going to have x successes and n independent trials. So I do this with the combination, right? So I have C n of x, and just as we saw before, n of x is going to equal n factorial over x factorial times n minus x factorial, where n factorial is n times n minus 1 times n minus 2 all the way up to 1, and of course 0 factorial is also equal to 1, so we don't count it. And just like I did before, for instance, I'm going to give you an example. 4 factorial, this is the way we denote it, 4 little exclamation point, and that's going to equal 4 times 3 why. PowerPoint does that, but it does. 4 times 3 times 2 times 1. And of course, we could do times 0, but it's just 1, so nobody does that. So here I have 4 times 3, which is 12, times 2, which is 24, times 1, which is still 24. So 4 factorial here is 24. Okay. So these combinations, these sequences are mutually exclusive. That means they can occur at the same time. So they're mutually exclusive. In other words, we're tossing our coin 10 times before we just do it. Right? I toss my coin, and I get. I toss my coin, and I get heads one time, tails the next, heads the next, and so on. But I can't get heads and tails on the same toss. I either get heads or I get tails. Okay. So an example is a fixed number of observations and 15 coin tosses. Or say we have 10 light bulbs taken from a warehouse. They're either they work or they don't. So, right here, heads or tails in each toss of a coin. Or the light bulbs can be defective or not defective. Right? In general, we call this success from failure. So in this case, if we're talking about heads, every time we have a head, we have a success. Every time we have a tail, it's a failure. Every time we have a light bulb that's not defective, we can call that a success. And when that's defective, we can call that a failure, or vice versa. Again, just 2 options. So the probability of success is P. That means the probability of failure is 1 minus P, since there's only 2 options and they have to add up to 1. The constant probability of each observation, the probability of getting a tail, is the same each time we toss the coin. Like 5. And of course, these observations are independent. If I get heads on the first toss, it doesn't affect the probability of heads, of me getting heads, on the second toss or any other toss. They're independent. Again, that's one of the definitions of our binomial probability distribution function. The outcome of one observation doesn't affect the outcome of the other observations. Okay, and here are some possible settings for our binomial distribution. A manufacturing plant labels items as either defective or acceptable. A firm bidding for contract either gets the contract or doesn't. A market research firm receives a survey. Either the customer will buy the product or they will not buy the product. And then finally, a job applicant, somebody applying for a job, either accepts the offer or rejects it, assuming they're giving the offer. Okay. So here's where it becomes a little more tricky, is our function, our algebraic function for our binomial distribution. First, we have the combination of n and x, right? So the probability is n factorial over x factorial times n minus x factorial times the probability of success to the x power times the probability of failure to the n minus x power. And of course, n minus x powers is going to be the number of failures, because n is going to be the total number of trials. So P of x is the probability of x successes and n trials, and the probability of success is P on each trial. X is the number of successes in the sample, and it can be anywhere from 0 to n. N is the sample size, the number of independent trials or observations. And P is the probability of success. So here we have an example. Right? Suppose I flip a coin 4 times. X is going to be the number of heads. Yes, X is the number of heads. I flip it 4 times, so N is 4. And the probability of heads on any given coin flip is 0.5, is 50%. That means the probability of failures is 1 times 0.5 or 0.5. X is going to be 0, 1, 2, 3, or 4. Heads can come up 0 times, 1 time, 2 times, 3 times, or 4 times. So in that case, right, I'm not doing it. Suppose instead of having a coin flip, I have some other trial where the probability of success is 0.01 and not 0.05. What's the probability of one success in 5 observations if the probability of success is 0.1? So in this case, x equals 1, right? I'm going to have one success. I had 5 trials, 5 observations, so n is 5, and a probability of 0.1. That's given. So here I'm going to have n factorial times x factorial times n minus x factorial, p of x, or p is 0.1, 1 minus p, this would be 0.9, and n is 5, and x is 1. Right? So here it is, I have 5 factorial over 1 factorial times 5 minus 1 factorial, or 4 factorial, times 0.1 to the 1 power, times 1 minus 0.1 to the n minus x power, or 5 minus 1. So here, right, basically I'm going to have 5 factorial over 4 factorial, or I'm going to have 5. And just to do the algebra, if I have 5 factorial, I'm going to have 5 times 4 times 3 times 2 times 1, which again times 1, and I want to divide that by 5 minus 1 factorial, or 4 factorial, so I'll get 4 times 3, and by the way, 1 factorial is just 1, so it's 1 times 4 factorial. I kind of ignored that, but that's because it's trivial. Okay, 4 times 3 times 2 times 1 Okay, so I have 5 factorial over 4 factorial here. Guess what? The 4's cancel, the 3's cancel, the 2's cancel, and the 1's cancel, and I'm left with 5. Just 5. So here I have 5 times 0.1 to the 1 is 1, times 0.9 to the 4th power. All right, I take my calculator, I calculate 0.9 to the 4th power multiplied by 0.1 times 5, and I get 0.32805. This is the probability of one success in 5 observations given a probability in each trial of 0.1. Okay, next we're going to talk about the shape of the binomial distribution. The shape of the binomial distribution is going to depend on the number of trials and the probability. So here, right, we have 2 trials, each 5 times for a binomial distribution. And the first one has a probability of 0.1, and the second has a probability of 0.5. And notice the one with the probability of 0.5 is skewed, right? But it's basically, it looks like this, whereas the one with the probability of 0.5 looks more symmetric. It kind of actually looks like a discrete normal distribution. Or if we can make it continuous, it could make it look like a normal distribution. Anyway, it's symmetric, where the one with 0.5 is skewed to the left towards 0. Okay, the mean and the variance of the binomial distribution. First, the mean is, we saw what the probability of a Bernoulli distribution is just mu. right, is just P. So here, for a normal binomial distribution, the expected value is going to be the number of trials times the probability. The variance, right, as we saw with the renewal, is going to be P times 1 minus P, but here we're going to multiply it by the number of trials, N. So the standard deviation will just be the square root of that. So the square root of N times P times 1 minus P is going to be the standard deviation, whereas the sample size P is probably a success, and 1 minus P, of course, is the probability of failure, because there's only two options, success or failure. So our characteristics here, right? Here we're going to see that when I have 5 trials and a low probability, that in general my standard deviation is going to be smaller than when I have a higher probability with those same 5 trials. And my expected value is going to be higher when I have 5 trials, so is my standard deviation. It's going to be 2.5 versus 0.5 and 0.76 versus 1.118. So the higher the probability with the same amount of trials, the higher the mean in general, everything else being equal, and the higher my standard deviation if the probability is higher. Here we have a binomial table. We have these in your book, or you have this in the book. And notice here the number of trials. It'll tell you the number of trials, 10. And if I remember correctly, the book has different tables for different numbers, and it kind of skips instead of going from 1 to 10. It kind of goes up. But anyway, we can see what the probability is. For instance, if I have 10 samples, I want to know x3 with the probability of 0.35. So x being 3 and n trials with the probability of 0.35 gives me 0.2522, or basically, right, with x3 coming up with the probability in that case is going to be 0.25. That's basically the probability of me having x3 in 10 trials with the probability of 0.35. Here, if I have 10 trials and I want to know what the probability of 8 is with the probability of 0.45, right, I come to the table, I look for x here, 10 observations, and 0.45, and that gives me 0.229. Now, in general, these are close to linear. So basically, if you don't have the number of observations that you want or the probability that you want on the table, you can basically go, like say it was 4.3, I can basically do this and assume it's linear and take the average of, or take 0.3 times the difference and add that to the lower number here. The next type of distribution we're going to talk about is Poisson. Now, Poisson was a statistician in the late 18th century, before we had computers, calculators, and all that other stuff. And he came up with a discrete distribution, right, used to determine the probability of a random variable, which characterizes the number of occurrences or successes of a certain event in a given continuous interval, such as time, surface area, and length. Right? So this is what you assume. I'm going to assume an interval is divided into very large equal subintervals. Right? Basically, I'm going to take the whole interval and I'm going to cut it in pieces, where the probability of occurrence of any event in any sub-interval is very small. So the assumptions that Poisson made is the probability of an occurrence of an event is constant for all subintervals. Right? So basically, the probability of hitting anywhere in a subinterval is constant, it stays the same. There are no more than one occurrence in each subinterval, and the occurrences are independent. That is, occurrence in one interval doesn't influence the probability of an occurrence in another subinterval. So he came up with this distribution function. Again, this was before computers and calculators. And this is the number he came up with. The expected number of events per unit is a parameter lambda that he named, which is constant, that specifies the average number of occurrences, successes, for a particular time and or space. So in this case, P of x is the probability of successes over a given time or space, given your lambda. The expected number of successes per time or space unit is going to be your lambda. And of course, E is the base of the natural logarithmic system, and that's going to be 2.718218, and it goes on forever. Basically, the decimals keep going, but it's basically the natural logarithmic system. So basically, right, oops, if you remember, hopefully from high school algebra or an algebra class that you're taking, right, darn it, doesn't want to let go. So if I have the natural log of x, right, and I take it to its exponent, so e to the natural log of x, right, is just going to be equal to x. And of course, if I take the natural log of e to x, I'll get x also. Okay. So that's just something, right, that happens in nature, the natural log. They knew about it, and Poisson figured out this distribution for, right, for discrete occurrences in the number of successes in a particular time or space, continuous. So the mean and variance of the Poisson distribution is as follows. The mean is simply lambda. And the variance is also lambda. This is one of the only distributions where the mean and the variance are the same. And of course, the standard deviation is the square root of lambda. Again, lambda is the expected number of successes per time or space unit. And most of the time you could do this by figuring out. For instance, we know that coin flip, right? I know that the probability of heads, even though it's binomial, not Poisson, but I know the probability of heads is 0.5, and therefore the probability of receiving tails is 0.5. The book has tables for Poisson also. For instance, here, if I want to find the probability that x equals 2, and the probability of a success, or lambda, is 0.5, so I look for lambda, 0.5, and here, right, I want to know what happens, or I want to know what the probability of x equaling 2 is with that. And here, the table gives me 0.07858. We can do it with the table, or we can do it with the formula that Poisson gave, right? The probability that x equals 2 is e to the negative lambda, e to the negative 0.5, times 0.5 squared, x is 2, over 2 factorial, which is just 2. I do the algebra, I plug in e to a negative 0.5 in my calculator, times 0.5 squared, which is just 0.25 over 2. and that'll give me 0.0758. I can do it with the table, right? Or I can do it with the formula that Poisson figured out. The Poisson probabilities, right? Here we can see the distribution. Here, x equals 0, right? Lambda, or x equals 0, p of x is 0.6, 1, x equals 1, and that's 0.3, and here x equals 2, it's 0.785, right? And then here 0.3 is 0.126, and then 0.4 is really small, almost 0, 0.0016, and then 6 and 7 are basically indistinguishable from 0. So basically getting 6 or making x equal to 6 or 7, the probability in those cases are essentially 0. Now the shape of the Poisson distribution is going to depend on the expected value, the probability of the number of successes, lambda, right? So here I have a lambda of 0.5, and we can see it's skewed to the left, right, to 0. And here we have a lambda of 3, and that basically comes out a little more to the right. Not quite symmetric or normal, but a little closer. The Poisson approximation to the binomial distribution, and this is one of those things you're probably never going to see again in your life, but it's possible. But here I'm going to let x be the number of successes from n independent trials with each probability of success p. The distribution of the number of successes x is binomial with mean n times p. If the number of trials n is large and n over p is only moderate size, i.e. n times p is 7 or less, this distribution can be approximated by the Poisson distribution with lambda equaling n times p, where the probability of the distribution by approximating the distribution is e to the n minus p over n minus p to the x over x factorial. Now, basically, this is basically taking lambda and making it np as long as n times p isn't too big. It'll approximate the Poisson distribution. I'm sorry, the Poisson distribution will approximate the binomial distribution. Okay, so we went on. The next type of discrete probability distributions that we're going to talk about is hypergeometric. All right. Here we have n trials in a sample taken from a finite population of size n. The samples are taken without replacement. We take something out and we don't put it back in the sample. It stays out. Outcomes of trials are dependent. In other words, since I'm not replacing the, or maybe and possibly for other reasons, but since I'm not replacing what I take out of the sample, the outcomes are dependent. So basically here, if I took out a 5 out of the sample, just for sense, that means it changes, right, the probability of 5 because there's one less 5 in there. So the outcomes of the trials are dependent. If for no other reason, because, right, we're taking the sample, we're taking stuff out of the sample without replacement. Concerned with finding the probability of x, successes in the sample where there are S successes in the population. I wish I wouldn't have used S because that's what we were using for sample size, but okay, here I have the probability or the hypergeometric probability distribution for probability. The probability, right, for the hypergeometric distribution is here. So I have the combination of S and X, where S is the sample size of the population and X is the number of successes in a sample. I'm going to have N minus S, where big N is the population size and S is the number of successes. And I'm going to have little n minus x, where little n is the sample size, and again, x is the number of successes in the sample, right? All over the combination of n, big N, and little n, where big N is the population size and little n is the sample size. So here, right, I'm going to have s factorial over x factorial times s minus x factorial times n minus s factorial times n minus x factorial times big N minus big S minus little n plus x factorial, all over big N factorial over little n factorial times big N minus little n factorial. So in the next slide, right, we're going to have the following. We're going to have s is equal to 4. So I'm going to have 4 factorial. Little x is equal to 2. So over 2 factorial. Okay. S is equal to 4, so I'm going to have 4 minus 2 factorial. I hope I have enough room. Times, this is factorial by the way, times n minus s, where big N in this case is going to equal 10. Minus big S, which is equal to 4. So I have 10 minus 4 factorial, or 6 factorial. All over x. And let me erase that. Over little n minus x, where here little n is equal to 3. And of course x equals to 2, so I just have 3 minus 2 factorial times, here we have big N is 10 minus the number of successes in the population, 4, S, minus n, little n, excuse me, which is 3, plus x, which is 2. Factorial all over, and see if I have enough room here. It's going to equal n factorial, big N factorial, and the population size is 10, so I have 10 factorial over little n factorial, and little n is 3, so hopefully 3 factorial times n, big N minus n, so that's 10 minus 3 factorial. Okay, so this is what we're going to do next. Here, let me do this, what's in the numerator here. is 10 factorial, which is the population size, over little n, which is 3, our sample size, factorial, times big N minus little n factorial, and big N is 10, and little n, which is the sample size, is 3 factorial. And basically you can do all the calculus. So I have 4 factorial over 2 factorial times 4 minus 2, which is 2 factorial, 2 factorial times 2 factorial, which is 2 and 2, 4, or 4 factorial. Here I have 6 factorial over 1 factorial times 10 minus 4, which gives me 6, minus 3 gives me 3, plus 2 gives me 5 factorial. I do all that. Over 10 factorial over 3 factorial times 7 factorial. 10 minus 3 is 7. So this is basically what I was doing. I have an example. I have 3 different computers are checked from a population of 10 in a department. 4 of the 10 computers have illegal software loaded. What is the probability that 2 of the 3 selected computers have illegal software loaded? So basically, I select 3. What's the probability that 2 have the illegal software, knowing that in the population, right, the sample or the probability is 0.4 or 4 out of 10. So here the population is 10, the sample size is 3, the number of successes here illegal is 4, and x is 2. So I do it. I'm going to have 6 times 6 over 120. It's basically doing the 4 times 2, 6, 1, 3. So that's 6 times 6 over 120, or 0.3, or 36 over 120. So probability that 2 of the 3 selected computers have illegal software is about 0.3 or 30%. Okay. If you have problems figuring that out and what I did in the last one, you can go back in the video. Hopefully it'll be clear. Okay. The next thing we're going to talk about are jointly distributed discrete random variables, or a joint probability distribution. Right? It's going to be used to express the probability that simultaneously x takes on a value of small x and y takes on a value of small y as a function of small x and small y. Or in other words, right, the probability of xy is the probability big X equals x, and the intersection of y equals little y. Right? The marginal probability distributions, which are part of the joint or come from the joint, P of x is going to be the summation of the probability of x and y over y, over all of the y's, and P of y is going to be the probability of x and y over all of the x's. Right? So the properties of this joint probability distribution of discrete random variables, I'm going to let x and y be discrete random variables with joint probability small x, or probability small x, small y. That is, the probability of x, small y, has to be between 0 and 1 for any pair of x and y. And the sum of all the joint probabilities, just like regular probabilities, have to sum to 1. So now that we have joint probabilities, we can talk about conditional probabilities, which is basically why we come up with the joint probabilities, or why we talk about joint probabilities. The conditional probability distribution of a random variable expresses the probability that y takes on the value of small y, and that the value of small x is specified for x. So the probability of y given x is going to be the joint probability of x and y, little x and little y, over the probability of little x. Similarly, the conditional probability of big X given y equals little y is the probability of x given y is the joint probability of little x and little y over the probability of little y. Okay, so if we have that conditional distribution, right, if the joint distribution of random variables x and y are said to be independent if and only if the joint probability distribution function is equal to the product of their marginal probabilities, i.e. the joint probability of little x and y would equal the probability of x times the probability of little y, right, for all possibilities of x and y. If that's true, then those two x and y are independent. One doesn't depend on the other. And if I have more than two variables instead of just x and y, if I have a bunch of variables, let's say x1 through xk, so I have a set of k random variables. They're independent if and only if, right, the probability of x1, x2, all the way to xk are equal to the product of the individual probabilities. That's the product of x1 times the product of x2 times the product of x3 all the way to the probability of xk. So basically I multiply them all together and that gives me the joint probability. That's to say x1 through xk are all independent of one another. They don't depend on one another. The conditional mean invariance for a conditional mean, the mean of y given x is, of course, the expected value of y given x. And that's just going to be the summation of all the y's given your x times the probability of y, of little y, given x. And, of course, the summation of little y given x times the probability of y given x. The conditional variance, right, there is it. It's all of the y's minus the conditional mean, y given x, all given x, right? So all my y's given x minus the mean of my y's given x. So basically that's a summation of my little y's minus the mean of y given x, all given x, times the probability of y given x. And that's the variance. Okay, so next we can talk about covariance. And we talked about covariance in chapter 2 regular, but here we do it in terms of probability distributions. I'm going to let x and y be discrete random variables with mean mu of x and mu of y. The expected value of x minus ux times y minus mu y is called the covariance between x and y. For our discrete random variables, right, we can do it with summations. I have the expected value of x minus mu x times the expected value of mu of y minus mu y, excuse me. So that's the expected value of x minus mu x times the expected value of y, or y minus mu y. So that's some summation of all my x's minus ux times all my y's minus mu y times the probability, or the joint probability, of little x and little y. So an equivalent expression, I can write this, right, if I do it. I have the expected value of x times y times the product of my means, mu of x times mu of y, or a summation of x times y, first with all the x's, and then with all the y's, times the joint probability of little x and little y, minus the mean of x times the mean of y, or mu x, mu y. That's the covariance. Hopefully it'll come a little quicker or a little clearer with the sample or the example we're going to give in a second. Once I have the covariance, I can figure out the correlation between x and y. Correlation is just the relationship between two variables, right? So the correlation of x and y, we're going to call it rho, and this is the Greek letter rho, right here. The Greek letter rho is going to be the covariance of x and y over the standard deviation of x times the standard deviation of y. Right? My correlation is always going to be between -1 and 1. If rho equals 0, there's no relationship between x and y, or at least no linear relationship. If rho is positive, there's a positive linear relationship between x and y. When x is high, then y is likely to be high. And when x is low, then y is likely to be low in those cases. A row of 1, positive 1, indicates perfectly positive linear dependency. Okay. So basically, if x moves up by 5%, y is going to move up by 5%. If rho is negative, right, that means we have a negative linear relationship between x and y. When x is high, then y is likely to be low, and when x is low, y is likely to be high. If rho is equal to -1, then we have a perfectly negative linear relationship. If x goes up by 5%, y will go down by 5%. Covariance and independence. The covariance measures the strength of the linear relationship between two variables. If two random variables are statistically independent, the covariance between them is going to be 0. The converse is not necessarily true. The covariance might be 0, but they still might have some dependence on one on the other. Okay. That's covariance and correlation. Next, we're going to talk about our portfolio analysis. Let's say I have a portfolio of 2 stocks. I'm going to let the random variable x be the price of stock A, and the random variable y be the price of stock B. The market value, W, for the portfolio is given by the linear function, excuse me. So A is the number of shares in stock A, little a is the number of shares in stock A, and little b is the number of shares in stock B. So if x is the price of stock A times x is the value of how much you own of x, and B times y, A times x is the value of how much you own in stock A, right? And B times y is the value of how much you own in stock B, right? So I add those up. A times x is how much I have in stock A, and B times y is how much I have in stock B, where x and y are the price of stock A, and y is the price of stock B. The mean value of W, right, I'm going to call it mu of W, is expected value of W, is simply the expected value of A times x plus B times y. And of course, A and B are just constants, there's a surprise. So the mean of W is going to be A times the mean of x plus B times the mean of y. So the variance for W is as follows. The variance of W is just A squared times sigma x squared times the variance of x plus B squared times the variance of y, sigma squared y, times 2AB times the covariance of x and y, how they vary together. So I can rewrite this using our correlation formula. And if you remember from just a couple slides ago, right, the correlation of x and y, I'm writing this horrible, but that's correlation, CORR, is going to be the covariance, COV, of x and y divided by the standard deviation of x times the standard deviation of y. That's x, so standard deviation of x over y. What that means is covariance is going to equal the correlation times the standard deviation of x and y. So that's what we have here, right? Instead of writing the covariance of x and y, I'm going to have the correlation of x and y times the standard deviation of x times the standard deviation of y. Okay. So let's say I have those two, right? And I'm going to invest in two types of funds. Right? The return per $1,000 for the two types of funds is as follows. Right? I have two funds. I have my passive fund X and I have my aggressive fund Y. If a recession occurs, my passive fund is going to lose $25. If, for my $1,000, if a recession occurs, my aggressive fund is going to lose $200. If the economy is stable in between, I'm going to make $50 for my passive fund, and I'm going to make $60 for my aggressive fund. If the economy expands, I'm going to make $100 for my passive fund and $350 for my aggressive fund. So the expected value of x, right, my passive fund, is going to be mu of x. It's negative 25 for recession times the probability of recession, which is 0.2. So negative 25 times 0.2 times $50 in a stable economy times the probability of a stable economy, which is 0.5. So that's 50 times 0.5 right here. Times 100 if the economy is expanding times the probability that the economy will expand is 0.3. So 100 times 0.3. So that means the expected value for my passive fund is $50. That's my expected return on the $50 for my passive fund. For y, my expected value of y, or mu of y, is going to be negative 200 in a recession times the probability of recession is 0.2 plus in a stable economy, I make $60 times the probability of a stable economy, which is 0.5, plus 350 times 0.3, which is the probability of an expanding economy, and of course I make 350 in an expanding economy. I add up all those with my calculator and I get 0.95. So my expected return for my $1,000 for X is $50. For Y, it's $95. Okay. The standard deviation, right, I know for my passive fund, I know the expected value is 50. So in a recession, I lose 25. So minus 25 minus the expected value, which is 50, squared, times the probability of a recession, which is 0.2. So that's negative 25 times negative 50 squared. So that's 0.75 or 75, not 0.75, 75 squared times 0.2. Here I have 50 minus 50 squared. Well, 50 minus 50 is just 0, so it doesn't matter. So 0 times 0.5, so that's 0. Plus 100 minus 50 squared, so that's 50 squared times 0.3. All right, so I have 75 squared times 0.2 times 50 squared times 0.3. I take the square root and I get 43.3. That is the standard deviation of the passive fund X. For Y, I know that the expected value is going to be 95. So in a recession, I lose 200. So 200 minus 95 squared, so that's 295 squared times the probability of recession 0.2. Here I have 60 minus 95. That is negative 0.35 squared times 0.5, the probability of a stable economy, plus 350 in an expanding economy minus 0.95 squared. So this is basically 255 squared times 0.3. I add up all these and I take the square root and I get 193.71. So the standard deviation for Y is 193.71. By the way, if I want the variance, all I have to do is square of x. If I want the variance of x, all I have to do is square 43.3. And if I want the variance for y, all I have to do is take the square of 193.71. And that'll give me the variance. But we calculated the standard deviation. Okay. So next, what I want to do is I want to calculate the covariance for my investment returns in x and y. My covariance of x and y is going to be in a recession, right? Negative 25 minus the expected value for x, negative 50, so that's 75. And I do the same thing for my aggressive fund, so I lose 200 in my aggressive fund minus the expected value of 0.95. Take negative 75 times negative 295 times 0.2. Then I do the same thing. Here I have 50 minus 50, which is 0, times 60 minus 95, which is 35, times 0.5, but 55 minus 50 is 0, so this second term is 0. That makes the algebra a little easier. Then I have the third, 100 minus 50. In an expanding economy, I make 100 in the passive fund. The expected value is 50. In my aggressive fund, I make 350 minus the expected value. My aggressive fund is 95. I multiply that by 0.3. I add up this, and I get 8,250, which means X and Y move together. In a recession, they both lose money. In a stable economy, they both make a little bit of money. And in an expanding economy, they make more money. Even though Y has more risk, it also has more reward. Okay. So here, right, I have the mean of X that we calculated, the mean of Y, the standard deviation of X, my passive fund, and the standard deviation of Y. We can see that Y has more risk than X. And we know that the covariance between the two is 8,250, which is positive, which means they move together. So suppose that 40% of my portfolio is in this passive fund X and 60% is in the aggressive fund Y. In this case, the expected return on my portfolio is 0.4 times 50 plus 0.6 times 95 or 77. The standard deviation of my portfolio is 0.4 squared times the standard deviation of X, which is 43.3 up here, plus 0.6 squared times the standard deviation of the aggressive portfolio, Y, 193.21 squared, plus 2 times 4 times 0.4 times 0.6, the probability or the percentage that I have in X times the percentage I have in Y, times the covariance, which is 8,250, and here my standard deviation is 133.04. Now notice here, right, the expected value of my portfolio is in between the two, skewed a little higher, 0.95, and my standard deviation is in between my two standard deviations. So the portfolio return and the portfolio variability are between the values for X and Y considered individually. So basically the standard deviation is between the two, the risk is between the two, and my expected return is between the two individual funds. So here we're going to interpret the results, which we kind of already have. The aggressive fund has a higher expected return, but it also has higher standard deviation, which means it has higher risk. The covariance is positive of 8,250, indicates that the two investments are positively related and will vary in the same recession. They both lose money in recessions. They both make a little bit of money in a stable economy, even though X makes a little more. And they both make more money in an expanding economy. And again, X makes more than Y, but they move together. And that is the end of the chapter. What we did in this chapter is we defined discrete random variables and probability distributions. We discussed the binomial distributions, first the Bernoulli distribution and then regular binomial distributions. We talked about the Poisson distribution. We talked about the hypergeometric distribution. We defined covariance and correlation between two random variables, and we used everything that we learned about expected return, covariance, and correlation, and we applied it to a portfolio investment. That's it. Have a good night or day if it's daytime. Thank you.